Good afternoon, everyone. A little progress each day adds up to big result. It's my pleasure to welcome everyone to 35th episode of Creative. To be active, we need creativity. Creativity keeps us active. So creative. Knowledge Square is our tagline. Sharing of knowledge increases our knowledge. Creative is a group of people who are very curious to gain the new knowledge. Creative focusing on non-textual, non-academic, non-syllabus related topic. Every Saturday, organizing a talks on different topics around 3 to 4 p.m. And we are live streaming our program in our YouTube channel. We have social medias where you can follow us for more details and updates. Today, the past and a gateway to the future. We grown up by listening Chandamama stories. Today we are going to listen science of moon, scientific way to study the moon. So to present this, we have Dr.Shyama Narendranath, scientist. To introduce today's speaker, we have Charan Patel with us. Over to Charan.
Thank you, ma'am. Myself, Charan Patel, CP, creative volunteer. I like to introducing today our speaker, Dr. Shyama Narendranath KC, ma'am. Ma'am is a scientist and completed PhD in Physics, ISRO Satellite Center and University of Calicut in Feb 2006 to May 2011 about X-ray studies of the moon. Ma'am published 40 plus papers in international journals. Ma'am spoken at several international conferences. Ma'am expert in X-ray spectroscopic and instrumentation. Ma'am received awards for Lunar and Planetary Science Career Development Award in 2008 and Chandrayaan-1 Payload Team Award in 2009 and European Geophysical Union Young Scientist Travel Award in 2015. Ma'am served as a reviewer in many international journals, proposals, etc. Ma'am have guided 2 PhD students and several MTech students and MSc students and BSc students. Welcome to our today's section, ma'am. Over to Supreme, ma'am.
Thank you, Charan. Thank you very much. Over to you, ma'am. Unmute you, ma'am.
Thank you very much, Charan and Supriya. And thank you to Creative team and especially to my colleague Srinath also for having me here.
Shama, check your audio, Shama. It's not reachable at all. Then please make sure your audio is reachable.
Okay. Am I audible?
Yes, ma'am.
Now it's better. Now it's better.
Okay. Yeah, thank you. I was just thanking everyone, especially Srinath, who's my colleague at ISRO, Charan for giving a very generous introduction, Supriya for your kindly making this possible. So I hope this interests you. Let me go ahead and share my screen. So today we'll talk about the moon. So is the screen visible?
No, ma'am.
Yeah. Okay. So
No,
it's not? Okay. Sorry about that. Just a moment. Yeah.
Yes, ma'am. Now
Is that
screen.
okay? Yeah. Okay. Yeah. So we'll talk about moon. So moon doesn't need any particular introduction to anybody, right? You all know very well because every day you see this on the sky, and it looks a little different every day. From the full moon to the new moon, as the moon goes around Earth, the illumination that it receives from the sun changes. And as you can see in this photograph, there is a waxing and waning from the new moon to the full moon. So this is a very familiar sight and that we see every day. So as human beings, we connect with the moon very much, is it not? Because you know, all the skies are always lit with this moon, and it inspires so many things, right? Not just science. So to say moon is therefore special to us, but scientifically speaking also, moon is very special. Now, so why is that so? If you look at our solar system, there are more than 200 moons in our solar system. Okay, so that way moon is just another satellite, right? Like, because there are like this 200 of them in the solar system. But in the inner solar system, if you look at the planets, none of them have a moon. So look at Mercury, look at Venus, they don't have moons. The Mars has two objects around it, which are its satellites, but they are irregular shaped and they are called Phobos and Deimos. They are captured asteroids. So in essence, if you look at the inner solar system where the planets are smaller, none of them have moons. And you go to the outer planets, they are huge planets. Like here, there is Jupiter. So if you look at the size of the satellites of Jupiter, you know, they are all like, the largest satellite of Jupiter is Ganymede. Its size is about 1/100th of the planet. Whereas if you look at Earth, Earth's moon is about 1/4. That's a huge difference, right? So that way, the formation of moon around Earth requires a special case. So for the outer planets, if you think of like how could they have formed, what we think is that when the planet formed, there is a lot of rock and debris, gas all around it, right? It's like the leftovers. So those leftovers then clump together and become these moons. So for these kind of very large planets in the outer parts of the solar system, this theory works well because they are small satellites. But for Earth and Moon, this doesn't set in because Moon is too big to form like that. So we need to make a special story for our moon. Now, when you want to make a scientific theory, what do you have to do? You first have to observe and see what are the pieces of evidence that you have to make a story, right? This is like trying to solve a puzzle. So you want to know how the Earth-Moon system formed. Then you need to look at what is that we have, what is that we know about the moon that allows us to make such a story. So there are mainly three things that lead us to the origin of the moon that we, as of now, we believe. So overall, moon has a lower density than Earth. So I hope you understand density. So what is density? No, all materials have different densities. That overall tells us what it is made of. So the Earth's density is about 5.5. Here we talk about density, we're talking about the overall density, because different materials, of course, different materials on Earth have different densities. But if you take the bulk of Earth, the overall density is about 5.5 gram per centimeter square. But if you come to moon, it is 3.3. So it has a lower density than Earth. So that's one factor. The moon rocks have lesser volatile elements. So volatile elements are those which change into the gaseous state very easily. Okay, so you know, water molecules, no? They become water vapor at 100 degrees Celsius, right? At normal temperature and pressure, at normal pressures. So on moon, such elements which are volatile are not much there when compared to Earth. So whatever we understand about the origin of the moon should follow these things that we know about the moon.
1 minute. There is an option upside. More option is there. There you can disable that annotation. More.
Can you do that?
Yes, ma'am.
You look at the oxygen isotopic ratios of Earth and Moon, that's identical. So the oxygen that we usually know of is oxygen 16. That is the oxygen that that is in the atmosphere. Most common oxygen that's in the
Sama voice is low, Sama.
But,
everybody is hearing her.
Hello?
Yeah, better now. Yeah.
Can you? Yeah, okay, thanks. But there are heavier oxygen also in the atmosphere. So these oxygens with mass number higher are called isotopes. So if you take the ratio of two isotopes on Earth and Moon, they are identical. So this is another clue to understand the origin of the moon. So why we are talking about oxygen isotopic ratios is because in the solar system, according to where the planet is formed, the oxygen isotopic ratios have some specific trends. So like if it is near to the sun, it would be, for Mercury, it's different. For Jupiter or Saturn, it's different. So by looking at the oxygen isotopic ratios, we know that Earth and Moon therefore formed at the same region in the solar system. So when early on people thought about how could Earth get such a big satellite, right? So one of the things they thought about was maybe Moon formed very far away in the solar system, somewhere else in the outskirts perhaps, and it was just going around, and Earth just captured it, just like how Mars got it asteroids. But then if you look at the oxygen isotopic ratios, you know that it's not so. Moon did form around the same region as Earth in the solar system. And also it's difficult to capture such a big body as Moon around Earth. So that those theories don't work. So what we think is happened about the origin of the Moon is like this. So when around 4.5 million years ago, when solar system had just formed and Earth was still forming, so you call it proto-Earth. So this is the proto-Earth, and a Mars-sized body happened to crash onto the Moon, onto the Earth, and a lot of the outer parts of the Earth, like its crust and some part of its mantle perhaps, they all became broken pieces and started orbiting Earth, and they all came together to form the Moon. So this is called the giant impact hypothesis, and that's what we believe that happened to the in the early part of Earth's formation, which led to the formation of the Moon. This theory was done in around 1975 by William Hartmann, and this is what we still believe. But only thing is, what we have to refine it about it is to understand more, like, okay, how exactly such a collision happened, at what angles it happened, how much of the Earth's material has gone to the Moon, how much of the impactor's material is on the Moon. So these things are important to really understand how that process happened, and to see whether what we now understand about the Moon can be explained by this giant impact hypothesis. So you see, Moon is indeed special because we had to make a special theory for the Earth-Moon formation, unlike for the other satellites. Now, okay, we made the story and all, but how do we actually know this? So the main or the only thing that we can do is to observe the Moon. So very early on, people used to look at the Moon with your eyes, right? And even by looking with the eyes, we can make out some features of the Moon. You used telescopes on Earth from the time of Galileo, and even today we look at the Moon with the telescope at different wavelengths. For example, we can look at the Moon using radio telescopes. We can look at the Moon with optical high resolution telescopes. So even now the ground telescopes are used, but early on that was the only thing we could do. Then we had spacecrafts from the 1950s when the space program started. There were first flybys that went to the Moon, then there were landers, rovers, and today we have returned samples from the Moon, and the United States, NASA is planning Artemis missions to the Moon, which will land humans in the south pole of the Moon. So that is how it has progressed, and all what we know about the Moon is from these observations. So as I said, if you just look at the Moon with the eyes itself, you can see that there are these dark and bright patches. So this is taken with a good camera by Girish. So here you can see these patches, which are called mare, because mare actually means sea in Latin, I think. So because long back people thought these are perhaps oceans, and they thought there are mountains on the Moon. So it was called mare and terra. And so we still call them highlands or mare. But now we know that these are results of volcanism on the moon. So we'll come to that. This is an image of the near side and the far side of the moon. And what is the thing that you notice here? The main thing is that all these big basins seem to be only on the near side of the moon. And on the far side, which is the side we cannot see from Earth, because the moon's face is locked onto Earth. The moon rotates so slowly, its rotation and revolution around the Earth are of the same order. Therefore, so we don't get to see this far side of the moon. All right, there is no dark side of the moon. So many times, you hear about dark side of the moon. There is no dark side to the moon because all parts of the moon do get sunlight at some point or the other. Like on Earth, moon also has night and days. It's just that it takes 14 Earth days on the 14 Earth days to make one lunar day. But all parts do get sunlight. But what we don't get to see is the far side of the moon. Can this drawing be stopped?
Yes, ma'am. There is an option there, annotation. Just
so, I just need to click them.
Upside there is a more option, ma'am. Just click on it.
Yeah.
There you get
Disable. Okay.
Yes, ma'am. That's it. Okay.
So how did these large basins form, or why is that the near side and the far side are so different, right? So what you see is a basic difference in composition, and that's why the colors are different. These highland regions are made of largely one kind of mineral and rocks, and these regions, which are more of volcanic origin, are darker in color and made of a different mineral. We'll come to that. So basically, when you look at the moon, you see a lot of craters. So let's get to those first. Craters are a very important feature in every planet, including Earth. So does anybody know a crater that's in India? So if you know, quickly write it in the chat. Otherwise, at the end of it, I'll ask you so that we don't lose time. So which is the crater in India? Okay, that's the question. Don't Google, just write what you know. So craters are, as I said, craters are formed by impacts. So there was one time in our solar system where the huge impacts used to happen. So impacts of collisions. How do we know this? Because on Earth, all this, because Earth has changed so much, right? From the time it started, Earth started to have life. So there is a biosphere. There are so many processes that's happening on the Earth. Earth has an atmosphere. So the evidences of such a era in the past has been completely wiped out from Earth, and we don't get to see this. But moon is a very near object. So whatever happened to the moon must have happened on Earth too. And so by looking at the moon, we actually know what happened to Earth at that point of time. And for this, craters are a very good way of understanding this. Here is an image of a crater. So it is just a deep pit that forms when a body collides with it. Right? You play marble in pits. So you make pits, small ones, you can make such small pits, right? Very easily. So this is a picture of the moon where this is like a bowl-like crater. It's a very simple crater, and the inside of this, can you see it's brighter, and there is a floor to the crater. So how this is formed, how this crater is formed can be really studied if you look at how the morphology of the crater or the shape of this crater. So this probably, looking at the diameter of the crater, we can make out what should be the size of the impactor. How deep this is also tells you with what force it should have struck, what angle, the symmetry here. See, it's very symmetric, right? So if you were striking something from a grazing angle or from the left, it would have become elongated. So by just looking at a picture like this, so much you can say about what kind of cratering must have happened. And here is another interesting thing, which is the most important thing here, to use craters as age indicators. So there are in this picture from LRO, LRO is a spacecraft around the moon. It's a narrow angle camera which takes really very high resolution images of the moon. You can see adjacent two craters. And what's the difference here? On the right side lower bottom, you can see a crater which has so many smaller craters over there, right? Whereas here it looks really fresh. So that is the point here. So now you know, like the bench in your class, if the first day that you go, if you had a very new bench, it will be very clean, right? So you can say that's a new bench. But when years pass by, students might scratch over it, etc., and looks old. So by just looking at the surface of the bench, you can say it's a new bench or an old bench. So just like that, here this part of the moon is older, whereas here something has happened that it looks fresh and new. Okay, so by just counting the number of craters on a surface, you can estimate the age of the surface. So this is a very important technique used in every planet, and moon is the reference for this, because it's only from moon that we have actual samples returned, and only if you really take rock pieces and test it in the lab can you say the age of that. So only from moon we have it like that. Therefore, moon is used as an indicator, as a reference of age in the whole solar system. Just another of those amazing images. Here you see tracks of stones that are rolling down a crater wall, which also indicates that there are some activities that might happen on the Earth. So these stones are coming from the central part of this crater, which is like a peak, like a mountain. So slow seismic activities, or like just like on Earth has earthquakes which shake up everything, moon also has moonquakes, but much lower in strength. So such things can cause these such stones to roll down. So this is an example image showing that. So overall, I just wanted to say that just by looking at images in detail, we can say a whole lot of things about the moon, right? So what did we look at now? So just by the color of the rock and the soil, we're trying to say that there seems to be mainly two different kinds of material on the moon, those bright areas and the dark areas. Then, there are a lot of craters on the moon, which means it's a very old surface. Then you compare surfaces, you can say that the surfaces which look fresh are young, and those are really battered with a lot of craters must be a very old surface. So that's the beauty of looking at it with pictures. But now if you want to, so this is just by looking at it. Now, if you want to know what is it made of, for that you need to do a little more understanding, right? I mean, just by looking at it, we cannot say what it is made of. For that, we need some other techniques. But the real basis of how we understand what the moon is made of is mainly coming from samples which were returned from the moon using mainly these 3 missions. So there were 6 Apollo missions which had humans on it. The first person who landed on the moon, right? Yeah. So who landed second? So write that in the chat box. So there were 12 astronauts who walked on the moon, and they brought back about 382 kilograms of Apollo samples. There were these lunar Soviet missions, which are robotic missions. So I have marked here from where all do we have samples on the moon. You can see it is all restricted to mainly, this range near the equator. And most of them happens to be in these darker regions. There is just one here on the rightmost part, which is the Chang'e 4, which was in the last few years, which was on the far side of the moon. And the very most recent return sample is from Chang'e 5, which returned 1.7 kg of rocks from the this region of the moon called the Oceanus Procellarum. Kirtika, you raised your hand. Do you want to ask something?
At the end of the session, we take questions, ma'am. Just you continue.
All right. So lunar missions are Soviet missions which were robotic. So they didn't have humans, but they sent robots and they took these samples and came back. So these are from the Soviet samples. And similarly for Chang'e 5 also. So there are no humans on it, but it is a robotic mission. And all of these samples, it is for those scientists who want to study it, it is distributed worldwide. As I said, mainly we know about composition from these samples. And as we get more and more such return samples, our understanding becomes more and more, because only in the lab you really can study it in very detailed manner, is it not? But then to understand, as you see here, it is only from a small region. We can't have so many missions that we collect from every part of the moon. So for that, we need satellites that go around the moon, take photographs, or look at the spectra. So spectra means just the reflected light in different wavelengths, and try to understand what is it made of in the other parts. But then our reference mainly is these return samples. When we talk about composition, would like to just highlight that what are we talking about? So you would have studied about the element carbon, right? So carbon, so these are two things, diamond and graphite, entirely different things. But there's one common thing between them, that both are made of carbon. So, but then they are entirely different. So what makes them different? It is the arrangement of the atoms. So on the right here, this is how a graphite is arranged. You have 3 of these atoms, carbon atoms, in different layers. Whereas this is how a diamond is arranged in a cubic structure. So though both are carbon, just the fact that they are arranged differently as a crystal makes the properties entirely different. So when you say composition, you can talk in terms of like, okay, I know the composition of diamond, that's carbon. But then if you just say carbon, that I found carbon on the moon. So then you have to ask the question, is it graphite or is it diamond, right? Only then can you say that what is the structure of it, and why is that important? Because this tells you how it formed, or what was the temperature, pressure, or what was the environment through which it went through to make this crystal. Okay, so you would know that diamonds don't form that easily, right? You need to dig very deep inside the earth to find diamonds. So why is that? Because it needs a very high pressure to form diamond. That's why it's so only then you can form this kind of crystal structure, and that's why it's so expensive as well. So when you find a diamond at a particular place, you know that it has gone through such high pressures. So do you understand now? So when we say composition, you can either say just the element, but then when you come to the mineral, it makes you also understand that what is the process that it has gone through. So you need both in essential. Now, one of the common minerals on moon is called the plagioclase feldspar. Forget the name, but the only thing you need to know is that what are minerals? You talk about mineral water, right? So you are familiar with the term. So when we in this context, when we talk about minerals, what we mean is it is a neat arrangement of atoms, which is what a crystal is. So naturally occurring such crystals are called minerals. So diamond is a mineral, quartz is a mineral, sodium chloride is a mineral. So any of these things, and all these minerals together make a rock. So there is no rock which is just only purely one mineral. So rocks are pieces of these minerals all come together. All right. So here, for example, these are all rocks which has this particular mineral series, but it looks entirely different, right? So by just looking at it, you cannot say that what is it made of really. So small changes in their composition make this difference. So that is the important thing. And here you'll see the difference. These are all terrestrial, whereas the rock here on the right down corner here is from the moon. So you can see the difference in color, in the texture. So that's how when geologists go on a field trip, they can pick the right rock. So one of the Apollo missions had a geologist, Harry Schmidt, if I remember. So he was specially recruited so that in these return samples they can really pick the right rocks, which were very useful among collection from the return samples. So these are some of the samples from the moon. This is I put it here to note some differences. If you go, so if you just go around and collect rocks on Earth, there or soil from Earth, you find many of these minerals. But on Moon, there are some very basic differences which makes it moon rocks. So that when meteorites from Moon fall on Earth, we readily recognize them because of these differences. On the left is a core from the Moon. So they did a core and brought it as it is. So its depth. We are able to also see as you dig deeper into the Moon how what changes. So basically there is change in density, the particle size becomes coarser, all that. But more importantly, there are two things, or in fact a few things which are part of the lunar soil which you don't find here on Earth. One is called the agglutinates. So you see these dark substances. So these are a result of heating up the lunar soil at very high temperatures because of micrometeorite impacts. So Moon, you see, doesn't have an atmosphere, right? On Earth, though in space, the meteorites keep falling all the time. So in all planets, you're getting showered by these meteorites. On Earth, they're stopped from, because we have an atmosphere and only very big meteoroids will reach the surface of the Earth. But on Moon, because it doesn't have a thick atmosphere, or the atmosphere is very, very, very thin, therefore, any meteorite that falls goes to the surface, it has a collision and it heats up the soil. So billions of years this has been happening. So these materials called agglutinates are found only there. That's a major difference. It's mostly made of, it has a lot of what is called nanophase iron. So it's a kind of it's a kind of material that can only be formed by this process. So that's very special in the lunar soil. Regolith breccias, you see. So breccias means 2 or 3 rocks which were pulverized because of the heat, and they come together to become another kind of rock. So this is again something that you find only on the Moon. And you do have it on Earth, but this particular process that leads to it is again impacts. This is a Apollo rock again, and you can see the two very different surfaces here. These are the dark surface and the surface white. And these are some of the latest samples from Chang'e 5. There is a glass bead here. So you see, it's very round and nice glass bead. So this is also a part of the soil. So glass beads are formed when they cool very rapidly. So there must be something that melted, and if it cools absolutely rapidly, it becomes glass spherules. So basically, because that decides the texture of the rocks. If you're forming a rock very slowly, the crystals have time to grow and becomes coarse grained. But if it's very quick, they become glassy. So that is a difference. Now, these kind of glasses are also again formed when meteorites impact and pulverize the surface, and you can form glass beads. And here again, a glassy material. All results, so glassy materials only point to the fact that there is some process that heats it up and melts the whole thing and again they form a coating on the surface. So these are all some special things that we understand only because we have brought return samples from the moon. Common lunar minerals are some of these. You don't have to worry about the names, of course, but only thing is that it's not that moon has any special mineral. These are all in fact, for all the inner planets in the solar system, it's basically all made of silicate minerals. So all of the inner planets have rocky substances which have almost the same kind of minerals. It is in the relative ratios of this is where the difference lies, and that actually matters a lot. Here there is a very high microscopic image of a section of a rock, and you can see the structure in it. Now each of this would be a different mineral. You call it classed. You see here, each of this seems to be a different mineral. And here is a further high resolution images of the elements, and you can see the red is magnesium, this blue is aluminium, there's calcium. So you see the structure in this. It's as you go to smaller and smaller scales, when there's a lot of detail in it. So anyway, so now in short, what is moon made of? If you ask, it's a complicated question, but overall we understand there are some major minerals that make up the moon. It has certain amount of the main elements like magnesium, aluminium, calcium, which is also found in the rocks on Earth. So overall, when we say composition, what we want to know is what are the elements that make it, in what ratios, what is the structure of the crystal, and where is it found? Because it matters whether you find it inside the crater wall, or you find it on a mare basin, or on the poles of the moon. So where it lies is also something that needs for interpreting how it is formed. Now that was from the return samples. Now spacecrafts go around the moon, right? And underneath, the planet is rotating. Here, of course, it's the moon rotating. So by remote sensing, we map the composition of the moon. So you see here 2 images. This is just a projection where you flatten it out. And here you see on the far side, it's quite different. So this is the amount of thorium on the moon. Just taking an example of one element. But you see this particular area seems to have a high concentration of thorium. So that's a special area called PKT, or Procellarum Creek Terrain. So nothing particular about the name. It's fine, you forget it. But what is more important are there are these concentrations of areas where thorium is very high, and thorium is a radioactive material. So that means that there is a lot of heat that can come from this radioactivity which is inside the moon, and it seems to be concentrated in this region. And in this case, this is titanium. So when we measure all this, what is our ultimate aim? One is you're mapping all this composition, what are the features on the moon, what processes are happening. This should all feed back to the original story we started with, right? That the moon, the Earth had a collision with another body, and that matter is now around Earth and formed the moon. In that process, by what we observe now about the composition of the moon, we should be able to relate it to that story and see whether it's correct. So we see that it needs some refining. Another important process that happened on the moon is called, again, it's a hypothesis. So until you prove something, you call it hypothesis, right? So this is also such a hypothesis that initially, so as we said, there was a big collision, and the leftover material from that is now becoming the moon. At that point, it's very, very hot. So we believe that at that point, it was so hot that most of the moon was molten. The only thing we don't know is how much was it molten. Was it like completely, this is a cross section shown here of a sphere, whether it was completely molten or half or 1/4, we don't know that, but at least you know that there was melting. And what happens when it melted? Then it slowly starts cooling and becoming a solid. So when you do that, heavier materials will sink to the bottom, right? That's something you know, isn't it? When heavy things come to the bottom, whereas lighter materials float on the top when you have a liquid. Same thing happens here when you form these layers. So the lightest part, which is the mineral we talked about, the white mineral that makes the highlands of the moon, that is the lightest of them. And that is the upper crust here, and it floats. So this is to say that most of the moon you saw was bright, right? If you remember the earlier pictures, most of it had the bright highlands. So according to this theory, this is how it was. Everywhere you had this structure with this whole surface of the moon covered with this plagioclase, which formed finally the crust of the moon. Then how did those so subsequently we had those mare basalts, which are formed by huge impacts that happened in the solar system, which altered the crust here, and deeper material from the mantle, which are volcanic material, which consisted of different minerals, came up and filled those basins. So that's why we have this different looking features on the moon. That's what we believe. But then you should ask, why only the near side, right? Most of the far side don't seem to have many of these. One assumption is, looks like the crust of the moon is not uniform everywhere. On the near side, it looks thinner than on the far side. But still, these are all open questions. It's not that we know everything about the moon, right? And another important question to ask is, does moon have a core? So, you know, Earth has a core, mantle, crust, that I've studied in your social science class, that we know quite well. But if you look at the moon, whether it has a core or not has been a question for many years. So right now we believe that it does have a small inner core, outer core, and some partially melted material here, and then this crust. And we said moon doesn't have an atmosphere, but actually it has a very, very, very thin atmosphere, as you can see here, and which is very visible in a particular element called sodium. Forget the details here, but just want you to remember that this is taken from the ground. So you look at the moon here, you see this is the part where the sun is shining on that very thin atmosphere, and you can see these very large tenuous atmosphere here, and also it has a tail. So this is the moon here, and if you look at it, this is actually fully made of sodium, because that's what is very visible from Earth, and there is a very elongated tail. So yes, moon's atmosphere is very thin, but it does have it, and it also has a long tail that goes anti-sun, away from the sun. So another very special part of the moon is the poles of the moon. So if you look at the future, all the internationally, all the countries plan to go to the south pole of the moon. So what is so special about the poles of the moon? Because these are very unique areas of the moon. Like shown here is the a part of the south pole of the moon. There are very special areas called permanently shadowed regions. And what is special about is that there are regions here highlighted in blue, which has never received sunlight. So it's been always dark there since it's like 4 billion years, it's been dark. So what does it mean? It's so cold, unimaginably cold. So some go down to 50 Kelvin, or lower. And then the ice, so we believe that there are ice deposits there, and it will carry very unique information because it's untouched for many billion years. This is a water ice at the poles mapped through remote sensing. with the moon mineralogy mapper on Chandrayaan-1. So you see these patches. It's very small quantity that's been mapped, but still we believe that by looking at how many such permanently shadowed regions are there, we believe there is prospect for a lot more. So in short, the future of the moon, currently the whole world is looking at the south pole of the moon because it contains the history of volatiles in the solar system. So not just about the moon. As I said, moon is a place where not much has changed in the last 4 billion years. You look at any other planet, there's a lot of changes that's happened, whether it's Mars lost its magnetic field. There are dust storms which change things. There are polar ice caps which changes. Venus, huge changes have happened. Venus, you believe there was an ocean and it's not there now. So, I mean, all planets have had huge changes, but moon has been a witness for the last 4.5 billion years ago without much things changing on it. Therefore, we believe that the history of how volatiles, so let's say water itself. So water is one of the main volatiles that we have on Earth as well as on the lunar poles. So how did moon get these? Is also very much related to how Earth got its water. Remember the story of the giant impact? So when you had a huge collision and it was also hot, Earth also must have lost a good amount of its volatiles. But then we have 75% of the Earth covered with water, right? So where did all that water come from? So to answer these questions, you must also look at the moon and how moon got it, because we are very close by, and whatever happened to the moon, there must be the effect on Earth as well. And what is the source of the volatiles there, and how does it lose it? There is a water cycle on the moon, as we know now. So what happens with as it goes around the sun in a year? And as a resource, it's an essential element for permanent settlements of the moon. So humans are now dreaming of making a permanent settlement on the moon, and if we have to do that, the south pole of the moon is one of the best places to do that because of the presence of water. Utilize the resources there. So that is what you call ISRO, or in situ resource utilization. For that, we need to know what is the form of water, whether it's just molecules, or do you have frost, or actually water ice, or is it mixed with the soil? Can we actually take it out and really make water which is in a usable form? And how economical it is, right? If you are really going to have build something on the south pole of the moon, it's a huge investment. So therefore, there are multiple aspects here that internationally many countries are looking at. And another thing is astronomy from the moon is also an exciting option, because you have a continuous undisturbed low light scenario. So if you have a permanent settlement there, and you can build telescopes there perhaps to study astronomical objects. Also, moon is seen altogether as a gateway. So if you were to go to Mars, which is a long journey, first if you had a permanent settlement on moon, you could go there, and from there proceed. So that's all I had. I just wanted to leave for students some reading material. You should try the Lunar and Planetary Institute resources, which has a lot of information, very nicely given. A blog by Jatan Mehta also updates all the latest events regarding the moon. And there are many resources if you all want to really try out how to do a research project. There is a virtual microscope collection where many of these Apollo samples are under a microscope. You can look at it. It's actually a virtual microscope. You should try it out. You can zoom in and zoom out just like if you had it on your table under a microscope. All the samples from Chang'e, Apollo, and the Chinese missions are all the details are given here. So if you really wanted to do some study, compare it with some rock that you find outside your surface, just even the looks of it. Go out, collect a few rocks, put it on your table, look at it carefully, and look at some of these lunar rocks. Write down what differences you see. What do you think that means? So these are all encourage you to look at some of these short projects. And if you are more, if you're not into research or looking at the moon just as an object of curiosity, also that's also something that people have been doing for ages, like the Van Gogh's famous painting of the starry sky with the moon. Lots of books on moon, and this is also something interesting. If you want to check out further, you should go to this moon gallery. So this is being now flown on one of the ISS, I think. So this is a gallery that artists from around the world are putting together for the first permanent settlement on the moon. So there are paintings, so this is for your handmade carving of an asteroid. There are very nice things that they're planning to take to the moon when we are there, but it's an art gallery really. So connecting to the moon need not be just with science. There are a host of things that you can do, and I'll leave with this. It's a very famous painting by Alan Bean, who is an Apollo 12 astronaut as well as an excellent painter. So thank you.
Thank you, ma'am. Hello, ma'am.
Yes, Supriya.
Unmute yourself, ma'am. If any questions, you can unmute and ask, madam. I gave an option. If any questions, you can raise your hand or you can directly ask, madam. Any questions? If not.
Hello, ma'am.
Ma'am, you muted, ma'am.
Ma'am, I'm audible, ma'am.
Yes.
Ma'am,
Who is this? Yeah.
ma'am, I'm Harshit. I'm working in education department. So I have one doubt, ma'am. Ma'am, in Maam mission, when the satellite was gone opposite side from the Earth, there was called as an eclipse mode, right, ma'am? In Chang'e mission, it was launched in other side of the moon. So how will the scientists will communicate with the Earth, ma'am? It will be also in eclipse mode, right, ma'am?
Yeah, so China has another satellite in L2 point, which they had already sent for communication. So there are some communication satellites of China placed at the right point for that.
Okay, ma'am. Thank you.
Any more questions? Okay. Giridhar sir.
Madam, good afternoon. This is Giridhar from Gauri Binod. Actually, ma'am, in last month, China's Chang'e lunar lander vehicles told that the first to find in the water on the moon, that to be very closely. What's the difference between this one and Chandrayaan 2, madam? From Chandrayaan first only we heard that there is a water molecule in that moon, but now China is telling that they are the first to find water on the moon, that to be very closely. Then what's the difference?
Yeah, okay. So Chandrayaan 1 moon mineralogy mapper had mapped the water on Earth, but on moon, but there was a slight difference because its energy band could only half see the line of the water line. So there was a slight ambiguity on whether it's just the OH or really H2O, because both have overlapping lines. China here, then of course Chandrayaan 2 recently had seen the full from orbit, had seen the full line, and we do confirm it is a water molecule indeed. But the Chinese, what they are saying is on the surface, without even touching it, like in situ, they can see this very much. So that is the difference. Remotely, when you do, there are some assumptions that you have to make. But when you are there and actually seeing it very close by, you can be more unambiguously say that, or more confidently give a result. So it is only in that manner.
Thank you.
Okay. Ma'am, it's
Yeah.
Shall we end it, ma'am?
Yeah, sure. Thank you.
Dhanvin, we have
Madam, Madam, you are going for vote of thanks, sir?
Yes, ma'am. Yes, sir.
Oh, no, just I wanted to have only one request, sir. Shama, just one general question and specific question. I missed it because disconnected. Suppose Earth didn't have the moon, what could have been the, simply, that not very complicated, what could have been the, like, overall the situation of the Earth? Second is the girl student especially, what is the prospectus in this lunar and planetary sciences? Maybe a short answer. It may be a big question, but still, thank you.
So if moon wasn't there, tides won't be there. So we believe, like one of the things we believe is that life on Earth itself happened because of the moon. Because if tides were not there, this pulling wouldn't have been there, and land, sea animals coming to Earth. So this is one of the possibilities. There are many things which would have been different. Just about the spinning of the Earth itself is because of the presence of the moon. So life on Earth, the spin of Earth are two things.
Yes, that's what I'm looking forward. Thank you for that answer. Second one.
And okay, especially for girls, what do I say? Like just like any other research, the prospects in this are indeed very high, because the fact is there is a lot of scope here. Because in future, our space program is only going to shoot up, right? So as you see that this is really an international effort. It is not just about the prospects in India. So abroad and with several countries, going to moon is not just about science. It's about exploration, having future prospects there. So there is a lot of scope in this area, and there is nothing about being a girl here that should stop you from doing science, especially planetary science.
Yeah, thank you. Nice answer. Thank you.
Okay. Any more questions?
Ma'am, I have a question, Dhanvin.
Yes, Dhanvin.
Ma'am, that one titanium of from Kaguya, I didn't understand.
I'm so surprised you remember titanium and Kaguya. That's very nice of you, Dhanvin. Okay, so titanium is stainless steel, right? Or iron kadai we use at home. So many things are made of titanium. Okay, so titanium is an important material that you get from Earth to make things, strong things. Okay, titanium alloys are used.
Rocket engine tank.
Yeah, okay. I said kadai because I thought. Anyway, so titanium is very much used. So the titanium on the moon, where all there is titanium on the moon, was measured by this Kaguya spacecraft, which is a Japanese spacecraft. Okay, so when they measured this from the orbit as it goes around, they had a camera which can see titanium. So they have mapped it like that and see that at some places there is a lot of titanium, some places very small amount of it. So if you want titanium, you should go to the place where there is a lot of titanium, right? So such maps are useful for that.
Okay, ma'am. Thank you. Ma'am, what about the vote of thanks?
What about the
vote of thanks?
Okay. Who is telling what?
Me only.
Okay, tell me, Dhanvin.
Sir.
ಸುಪ್ರಿಯಾ ಅವ್ರ ಹುಡುಗನಿಗೆ
sir.
ಹೇಳಿ vote of thanks ಮಾಡಕ್ಕೆ.
Yes, sir.
Yes,
Dhanvin, we are at the end of this session. You can hand over it.
Yes, ma'am. Hi, everyone. My name is Dhanvin Ram. Hereby, I take this opportunity to honor Mrs. Shyama Narendranath, ma'am, who has spared their precious time to educate us about the moon amid of their busy schedules. I thank you, ma'am, on behalf of our participants, students, guests, and coordinators. You have shared our wonderful experiences on and educated us about Apollo mission compositions, compositions of elements, titanium from Kaguya spacecraft, and all. Thank you, ma'am. Thank you, ma'am. We all wish you more success for all your future projects and endeavors. Thank you, Srinath sir, Supriya ma'am, and all volunteers for the wonderful platform of knowledge through creative group and its educational activities. Thank you. Jai Hind.
Excellent.
Thank you, Dhanvin.
Thank you, Dhanvin.
You're welcome, ma'am.
Shama, thank you so much. It was a wonderful talk. So much. I also learned a lot. Thank you.
Thank you, Srinath, again. Yeah, thank you.
Thank you, madam.
Thank you,
Thank you,
Supriya.
thank you. Thank you, madam.